Right. Good evening, everybody. I hope I'm audible. Right. So this is day number 3 in our session. Day number 3 in our session. And we have already finished how much? 40 MCQs, 2 structured essay, 2 essays. So today, 20 more MCQs, 1 structured, 1 essay. Clear? 1 structured, 1 essay. Right. Earlier, so I'm sure you all have finished work, joined. Look at this. Right. Here you are given a brilliant circuit. Absolutely brilliant circuit. Where? If you look at this, consider the following statements. Consider the following statements. Make potential difference. About the potential difference. There you go. Potential difference across the XY circuit P and Q. Across the XY circuit P and Q. Look at this. Internal resistance. There. Same EMF, negligible internal resistance. Right. Look at this carefully. Now, observe. What's happening here? This is positively charged, this is negatively charged. So charges will travel, then the charges will come back. If you look at this, current will travel from the positive terminal. These are open terminals. If they are open terminals, current can't go through this. So current won't go there and stop and wait. Clear? Current will keep going through this. So current keeps on going. There you go. Right. Now look at this. They are asking potential in both circuits are equal. Are they equal? Let's see. Here, this energy is divided among that and divided among this. Right, V1, V2. Same charge will. What here? So here also Q divided by 10, here also Q divided by 10. Potential differences are equally divided. So potential difference across XY in both circuits are the same. So let's see. This is Q divided by 10. Q divided by 10. Exactly half. So this is half. This is exactly divided half. So here also the potential is going to be E divided by 2. Potential here is accepted. Right now? Okay. Now look at this. Right. Equal resistors. Potential difference is equal to I times R. I'm applying across 100 ohm resistor. 100 ohm resistor. Okay. So potential difference here, if you want, I'll take it as V1 V1 is equal to, remember, same current will pass through, I times 100. So here you can say I times 100 is the potential difference here. What about the potential difference here? I'll take these two terminals as V2. If you take as V2, I times R. R is going to be 100. Same current R. Now what can you say? V1 and V2 both are what? 100I. 100I. V1 and V2 both are same means V1 and V2 is voltage. So what can you say? Circuits are the same. Right? So equal resistors, voltage will equally divide. Voltage here and voltage here, if the batteries are the same, will be the same. Clear no? Let's write below. One by one, let's go. Let's write. There are equal capacitors and two equal resistors. There are two equal capacitors and two equal resistors. This means the supply voltage will equally divide. The supply voltage will equally divide. Supply voltage will equally divide. Right. Supply voltage will equally divide. Okay. There, I might erase that. Right. What's your next? What's your next statement? Next statement, if the voltmeter with finite internal resistance is connected across XY, it will read a steady non-zero voltage. Steady non-zero voltage. Now, look at this. Voltmeter with finite internal resistance. Yesterday, can you remember I told you? If in the voltmeter, there is no finite. Finite means there is nothing through. It will be a steady non-zero voltage only in Q. Steady non-zero voltage only in Q. Right. Look at this carefully. Here, right. There you go. Observe this now. Now, if you connect, what will happen? It has finite. Carefully. Now what will happen? Now remember there is a capacitor connected here. So now the connection, no, effective resistance will reduce. If effective resistance reduces, voltage across effective effective resistance is smaller means, you remember potential divided. Effective resistance is smaller means we voltage smaller potential difference. One small sentence there. A resistor parallel to, sorry, when we connect the voltmeter parallel to the resistor, when we connect a voltmeter parallel to the resistor, clear, right? Okay. So go back, right? Go back again, don't worry. Here now, first point. First point. Potential difference across X and Y in both circuits. Explain again. Divided by 2. Here, same resistors, voltage will equal. E. So this is also E over 2. Clear? No? Right. Statement A is correct. Right. Second one, if the voltmeter with finite internal resistance is connected. What do you mean by finite? Finite means there is a resistor. There is a resistor means current will pass through this. Now, if current pass through that, here and here they are parallel resistors. Resistance reduces, the potential difference will also what? Reduce. Potential difference will also reduce. Right? No? Okay. So now, potential difference reduces. So voltage here will be reduced but steady value. Reduced but steady value. Now here the thing is this, the beauty of a capacitor is if you connect a resistor parallel, already now this is charged, this has a voltage. If you connect a resistor parallel, this will discharge. Still photos. You press the flash and you wait for some time. Then after some time it will give a flash. Discharge is taking place means there is a capacity. So remember, then suddenly reduce. Here all reduce. Now, is it going to be steady or non-steady? It is non-steady. If a voltmeter with finite resistance is connected across X voltage is only, this is correct. Clear? Understood? Okay, let's write. Let's write. When there is a when there is a resistor connected parallel, we obtain a constant voltage. But when we connect the capacitor, the capacitor will discharge. The capacitor will discharge. And the volt will be. Okay. right? Okay. So when we connect the capacitor, the voltage drop will not be steady. Okay, right. If the voltmeter is ideal, both circuits will provide the same voltage drop reading across XY, right? What do you mean by that? If I have ideal voltmeters means no current passes through. No current passes through means here the effective resistance will be the same. Here there is no current passing through. This voltage and that voltage both will be what? Same. Both the voltages same. So here statement C will be correct. Statement C will be correct. So what can you say here? All ABC are true. All ABC are true. Like since we had some, I think, internet issue, what I'll do is I will explain this again quickly. Right. Yeah, if you look, come back again. First one, potential difference across XY in both circuits are equal. So here, this voltage, if I show it to you all, cafe look. Now here you have the battery. Here you have the capacitor. Battery EMF is E, 10 microfarad is here, 10 microfarad is here. Here if you look at this, they want you to find the voltage here. What happens is equal capacitors means voltage here is E over 2, voltage here is also E over 2. Right. Now here if I connect and I have two resistors, is 100 ohm here, terminal connected, again equal resistors, voltage drop here is E over 2, voltage drop here is what? E over 2. Clear? E over 2. Right. Now what happens is, if I connect, now this is the first one. The first one, statement A correct. Statement A correct. If you want, you can take a photograph of the first one. Right. Statement A correct. Right. Statement 2. Statement B. Right. Statement B. What are they talking about? Statement B. Statement B. Right. Same thing is there. Here 10 microfarad, here 10 microfarad. 10 microfarad, 10 microfarad. Now don't forget they are already charged. You have charged this to a voltage E over 2. This voltage is E over 2. Now you have terminals. We are connecting a finite voltmeter. Finite voltmeter means here there is a voltmeter. Here there is a voltmeter. Where there is a resistor. Here you have resistance here. Don't forget this is 100 ohm. This is 100 ohm. Now you know the voltage is divided. Now I connect a voltmeter here with finite resistance. Tell me now what happens. Effective resistance will become smaller. Effective resistance becomes smaller means potential difference will drop. So effective parallel circuit, no. Parallel R effective will be lesser than 100 ohm. R effective will be lesser. Lesser means potential difference will be less than E over 2. But don't worry, if I plot the graph here, potential difference versus time, lesser value but constant. But now if you go here, now be careful. If you go here, don't forget, this is already charged. Just like in a camera flash, the moment you put the flash, after some blinking, suddenly the flash will come. That sudden flash means from here there is going to be a discharge. That means sudden discharge will take place. Now when discharging occurs, carefully look, high voltage, now your camera flash, does it flash and wait for a long time? No. Flash will come and reduces. Go on. There'll be a drop. What about the current discharge? Current discharge also will be same. So steady constant value is there only in Q, not in P. This is what you should draw. So if I go back, statement B is also correct. Statement B is also correct. Right. Statement B is also correct. So B statement is correct. That's the circuit. This is the idea. Okay. Now, in any what you call review book, it's not taught like this. Complicated words are used to explain something very simple. Very simple. Your phone flash, remember. When you connect a capacitor across a resistor, sudden discharge will take place. From high voltage, voltage will reduce non-linearly. These graphs are not there in your syllabus, but knowing the graph is important for you. Yeah. When you go to university, you learn this in detail, but this is enough. You know it's not constant. Right. Now, part C. What is part C? Part C, here capacitor is there, here capacitor is there. If I connect the ideal voltmeter, ideal means infinite, that current is going to go through, or the charge is going to go through straight. Just like in circuit number 1. Here current is 0 means no discharge. No discharge. No discharge means what? Voltage reading? E divided by 2. Here E divided by 2. What about the other one? Here when I connect it, resistors are equal. Resistors are equal. If I connect a ideal voltmeter here, no current passing through. What can you say about the voltage? This voltage will divide equally. E divided by 2, E divided by 2. This is similar to statement A, which is correct. Similar to statement A, which is correct. Okay, now? Right. So therefore, A, B, C all are correct. A, B, C all are correct. Okay, right. I think we took half an hour for this with the interruptions. Can't help, we'll move forward. Okay, right. Today. Right, okay. Second MCQ. Second MCQ. Get this carefully. A horizontal table is rotating with a uniform angular velocity about vertical axis passing through the center. Mass M is at rest. Mass M is at rest. Mass M is at rest. Now when mass M is at rest on the table without slipping, observer A is sitting on the table while the observer B is standing. Observer B is standing. Right. What are they asking you? The total horizontal force on M. Now remember, if you're rotating with this, with respect to you, you will observe this to be at rest. Imagine you're going on a merry-go-round, your friend is also on a merry-go-round, with respect to you, your friend is also at rest. So with respect to him, he will observe resultant force is 0. But if you're outside, we know when you rotate, there should be a centripetal force. Somebody should provide the centripetal force. Who is providing the centripetal force? Friction will provide the centripetal force. So B will see a force to the center, A will see no force. Therefore, statement 1 is correct. Statement 1 is correct. Okay, that's right. That's right. A will observe no relative motion on B, on M. A will observe no relative motion on M. No relative motion on M. This means with respect to A, the resultant force is 0. With respect to A, the resultant force is 0. With respect to A, the resultant force is 0. But a person standing outside, But a person standing outside will observe a centripetal force to the center. Will observe a centripetal force to the center. Will observe a centripetal force to the center. Right. Okay. Moving on. Moving on. Carefully look. In an experiment to measure the thermal conductivity, a long bar of material is normally used. This is to obtain, now interesting, a long bar of the material is normally used. This is to obtain steady state condition, achieve higher heat flow, obtain practically measurable temperature difference along the bar, make lagging easier, ensure parallel flow of heat along the bar. Very good question. First, think about heat flow through a rod. Think about heat flow through a rod. Assuming it is properly lagged. Assume it's properly lagged. That means there's going to be axial flow, axial heat flow, axial heat flow. What is the equation for axial heat flow? Q dot T equals K times A delta theta over L, or L. This length we can take L. Look at the board carefully. Look at the board carefully. Now, when we increase the length, obtaining steady state condition, whether it's a long rod or a short rod, that's not the problem. Steady state means every cross section the temperature is constant. Every cross section the temperature is constant. Length has no effect to play. You have to make sure that every single molecule is vibrating for that cross section at a particular vibration. Therefore, temperature is constant. No effect. Achieve higher heat flow. Now, somebody looking at this will say, sir, L is increase means temperature gradient reduces. The problem, no? Temperature gradient reduces means Q dot will reduce. So that will not achieve higher heat flow. Obtain a practically measurable temperature difference. Nice. If you can make this constant, material is also constant, area is also constant. Look at this carefully. If you cross multiply, delta theta is proportional to delta L. Greater the length, greater the temperature difference. Greater the temperature difference means delta theta can be measurable. This is the reason. Third one is correct. Understood? So I'm sending a constant heat. K is constant, A is constant. That means if I take this to this side, delta theta proportional to L. That means when L increases, temperature difference will also increase. Remember, temperature difference is the most important one. Greater the temperature difference, greater, easier to measure. So statement 3 is correct. Third one is correct. Understood? No? Right. Next one. Next one. A liquid and its vapor. Liquid and its vapor. Tell me, liquid and vapor means what? Saturated. Liquid and its vapor. If a liquid is in contact with its own vapor, it's going to be saturated. It's going to be saturated. I'll just close this. I don't know. Close. Let's see. Right. The volume of the vessel is expanded slowly at a constant rate. Saturation. Then yesterday's practical, you might remember piston cylinder. Piston cylinder. Piston cylinder here, saturated. Tell me, people who remember yesterday's graph. Saturated vapor, if you increase the volume by keeping the temperature constant, will the saturated pressure change? Answer is what? No. Saturated pressure will not change. Right. Nice question. Nice. So here, the volume of the vessel is expanded slowly at a constant temperature. Temperature does not change. You must remember the graph that you learned. TV graph. TV graph. Wherever you learned, you will learn this. This is unsaturated vapor. Unsaturated vapor boils Saturated vapors do not obey Boyle's law. That means even if the volume increases or reduces after saturation, saturated pressure will not change. So vapor pressure increases linearly with the volume, wrong. Vapor pressure decreases linearly with the volume, wrong. Vapor pressure remains constant, correct. Number of vapor molecules per unit volume increases, wrong. Saturation occurs, saturation occurs. Tell me what happens. Dynamic takes rate of condensation. That means number of molecules here will never change. Okay, right. Kinetic energy of the vapor molecule decreases. Wrong, no. Temperature is constant means kinetic energy can't change, no. Wrong. Correct answer is answer number 3. Right there. Consider the PV diagram. Consider the PV diagram for a saturated vapor at constant temperature. For a saturated vapor at a constant temperature. The saturated vapor pressure will not change. The saturated vapor pressure will not change. Even if the volume reduces. Even if the volume reduces. Right? No? Okay. Right. Look at this carefully. 10 identical machines. 10 identical machines. That means, let's say, one machine, intensity, let's say, is I. 10 machines, 10 I. In order to decrease the sound intensity level by 10 decibel. Sound intensity means beta. What? Beta. Number of machines should be turned off. Let's say initially 10 machines are there. Finally, X machines are there. So X machines means X times I, right? So initially 10 are there, finally X are there. So how much have I switched off? 10 minus X. Look at this. Higher intensity, higher beta. Beta 1 is 10 log. 10 I reference intensity. Reference intensity. Beta 2 log xi divided by IO. IO is reference intensity. Normally for your here, threshold of hearing. All of that. Difference. Difference is 10 decibels. Subtraction means log division. Of your easy, huh? 10 log xi over IO. Who is common? Who is common here? Still lagging. Check one. Can you all hear? Yes or no? Lagging. Answer now. No, can you all hear? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can you all hear? Can you hear? No? I, I will keep my YouTube on here. I will keep my YouTube on video. Then I can hear no, exactly. Right. We continue the work. Okay. Have a look. One machine intensity is I. One machine intensity is I. 10 machines intensity is 10I. Finally, let's say there are X machines on. X machines on means XI. XI. Now what? Now initial beta is 10 log 10I over I naught. What is IO? IO is what? Threshold of hearing. What is beta 2? 10 times XI over IO. XI over IO. So XI over IO. So the difference here is the 10 log. 10 decibels. 10 decibels. Clear? Now look. Now look. Here, difference is given as 10 decibel. Difference is given as 10 decibel. When you are doing a log subtraction, take the 10 out. Then what do you have? Log 10I over IO minus log XI over IO. XI over IO. Log subtraction means log division. That means this divided by that. 10, 10 cancel off. I can put 1. Log division, look at this carefully. 10I over I naught divided by XI over I naught. I naught cancel off. There. Now what? Here you have, look at this carefully. I'll do it here as well. 1 is equal to log 10 divided by x. How do you remove the log here? Log 10 means here goes 10 to the power 1, 10 divided by x. X is equal to 1. So finally you have one machine on. So how many machines have you removed? 10 machines are there. Finally only one machine. How many machines are removed? 9 machines are removed. 9 machines are removed. Clear, no? Now okay. You can put in the chat. Can you all hear? Okay, no? Right. Okay. Moving on. Moving on. Okay. Maximum focal length. When do you have a maximum focal length? When light rays are coming from infinity. Maximum focal length means power is minimum. Minimum focal length means from the near point, power is maximum. Don't forget. So here you go. Light rays coming from infinity converge on the retina. That means what can you say about the focal length of the eye? Focal length of the eye is going to be 2.5. So diameter of the eye is going to be 2.5 centimeters. Diameter of the eye is 2.5 centimeters. Clear? 2.5 centimeters. right? Okay. Then what? Then what? If the near point is 25 centimeter, the minimum focal length of the lens will be minimum focal length. Right now you can do. I is here. Object is kept here at 25. Object is kept here at 25. What is happening? Light rays are coming. Light rays are coming. Where will it converge? It will converge on the retina. What is the distance to the image? Image is 2.5. Now you can apply lens equation. Okay, no? Now you apply 1 over V minus 1 over U equals 1 over F. Okay. 1 over V. 1 over V is minus 2.5. 1 over U. 1 over U is 25. Focal length is F. Simplify it. Simplify it. You know? 10 over 25. 1 over 25. Focal length 1 over F. F is equal to minus 25 over 11. Minus 25 over 11 is 2 point. For 30 you have 2. For 70 you have 6. 2.26 something will come. 2.26 means approximately 2.3. 2.3. Write down carefully. Write down carefully. Okay. Right. Okay. You know? Right. Moving forward. Moving forward. MCQ number 7. MCQ number 7. Now these are also easy. Very easy. Like my name. In the circuit shown, V represents a ideal. 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 What does ideal mean? Ideal voltmeter mean? Put in the chat. Put in the chat. I'm looking at the chat now. Quickly put. What do you mean by ideal voltmeter? Is current passing through? Is current passing through? Yeah, infinite resistance. What else? No. I want to know what happens. Does current pass or does not current pass? Is current passing or not passing? Passing or not passing? That's all I want. In your head, remember electricity is very easy. Don't complicate it. Passing or not passing? Zero current. Very good. Very good. Right. So no current is passing here. No current is passing there. Right. A variable resistor. A variable resistor means we can change the resistance. Here, we can change the resistance. Right. Can be varied from 0 to 100. Where is the variable resistor? Here is the variable resistor. Can you see the sign? Variable resistor. Right. As R decreases, R is reducing. So from 10,000, I am reducing. 10,000, not increasing. 10,000, I am reducing. the voltmeter reading will approximately vary. Right. What is happening? Whatever happens, current won't go across this. Whatever happens, current won't go across that. Right. Yesterday's work, small reminder. If there are two resistors like this, if the voltage here is V0, I taught you all a small shortcut to find the voltage here. What's the shortcut? Resistance into total voltage. Resistance into total voltage divided by the addition. Okay, no? Divide by the addition. You remember this, no? Right. Now, from 10,000 to 0, I am reducing. 10,000 to 0, so 750, 250, 100, 100, 10 volts on top. Right. Let me go back to the board. Right. So a lot of, yesterday we didn't use the board, today we are using the board. Very good. Right. Here there is a resistance. 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 Here is your variable resistance. Among this, you have your voltmeter. Plus and minus 750, 250. Plus and minus 750, 250. Plus and minus 750 ohm, 250 ohm. Here 100, 100, 100, 100, 100, 100, 100, 100, 100 ohm, 100 ohm. Here grounded. Here plus 10 volt. Now here there is nothing, no. So this is also plus 10 volt on top. Here grounded, 0 volt. Here also 0 volt. Right. Now, this is reduced from 10,000 ohm to 0. I'm reducing. Don't be in a hurry. Think and answer. If there is 10,000 ohm here, what can you say about the effective resistance? Now, some of you already say, sir, let's find the effective resistance. This is MCQ, no? 1 over 100, 1 over 10,000. Who is bigger? 1 over 100 or 1 over 10,000? Quickly tell me. 1 over 100 or 1 over 10,000? Quickly tell. Huh? 1 over 100 or 1 over 10,000? Tell. Which one? So which one is larger? 1 over 100 is larger. Very good. Simple. So if I take the effective resistance here, 1 over R equivalent is 1 over 100 plus 1 over 10,000. This fellow is bigger. So approximately 1 over 100. That means approximately the effective resistance is 100 ohm. Okay. MCQ means the brain you should use. Now you have 100 ohm here, 100 ohm there. Now use your today first MCQ. We did for half an hour today. That you should be expert now. 100 means what will happen to the voltage? Quickly tell. Voltage is here to here. Here 0, here 10. 0, 10 means how much? 10 volt. Is current going here? No. No current is going. Here to here. What can you say about the voltage? This whole thing is 100. This was 100. What can you say about the voltage here? What can you say about the voltage here? Put in the chat quickly. Quickly tell. Will be half. Very good. That means this voltage will be exactly half. Now look. Exactly half means there. Exactly half means here 0 means here plus 5. Here plus 5. Now what can you say here? Is current going this way? No. Right. Then potential divider theorem from the bottom, from the 0, always from the 0. Now what do? You need to find the voltage here. How are you going to find the voltage there? Look, resistance into total voltage, resistance 250 multiplied by total voltage divide by the addition 750 250 750 plus 250 750 plus 250. All right, some of you all are new, you all were not there yesterday, today you all are here. 750 plus 250 is what? 1000. 2500 divided by 1000, how much? 2.5. 2.5 where? From 0, 2.5 plus 2.5. Now they are asking the voltmeter reading. Don't be in a hurry. How do you find the voltmeter reading? Look at the positive terminal value. Look at the negative terminal value. Potential difference is positive terminal value minus negative terminal value. 2.5 minus 5 minus 2.5 volt. You will say, sir, minus? Yeah, center 0. One side positive is also there, other side positive is also there. Clear, no? So here minus 2.5 value. Quickly write down. Okay, right now. Now here, I'll erase here itself and do. Here itself I erase and do. Right. Now I'm going to erase this. I'm going to erase this. I'm going to erase this. I'll erase this. I'll erase that. Ayyo, in vain. I'll keep it. Right. Now what? Finally, 10,000 to 0. Now tell me, when this becomes 0, 0 ohm, how do you find the effective resistance? 1 over 100, 1 over 0. Tell me now who is bigger, 1 over 100 or 1 over 0? Tell. One over 100 or 1 over 0? 1 over 0 is bigger. 1 over 0 will be bigger. 1 over 0 is what? Infinity. But wait. This fellow is smaller. So 1 over R equivalent is approximately 1 over 0. Turn upside down. R equivalent is approximately 0. And right. That means the effective resistance here is 0. Clear? Effective resistance here is 0. Wait. Effective resistance here 0 means, what is your potential drop? You will say, sir, potential divide, I know. Resistance into total voltage. 0 times 10. 0 times total voltage 10 divide by the addition 100 plus 0. 100 plus 0. What's your answer? 0 volt. Understood? Will something happen here? Nothing happens. Nothing will happen there. Because yawn is changing. Here, no? Here voltage 250 into 10 divided by addition. Same. 2500. 2.5. And now what is the potential difference? Potential difference is positive terminal minus the negative terminal value. 2.5 volt. So what's happening? Resistance changes from 10,000 to 0. 10,000 to 0. Voltmeter will change from minus 2.5 to positive 2.5. Minus 2.5 to positive 2.5. Clear? Understood? Fun, no? Circuits are fun, no? Right? Right? So let us select minus 2.5 to positive 2.5. Answer is answer number 3. Okay. Right. Okay. Moving on. Happily moving on. Right. A suitable value for R to bias a silicon transistor in the active mode. Now in transistors, there are 3 modes. Saturation mode, active mode, cutoff mode. Okay? Saturation, active, cutoff. Now in the cutoff, VCE, this is called base collector emitter. Base collector emitter. Right. Cutoff region, VCE is equal to VCC. Wait. What is VCC? This is your supply voltage VCC. Here grounded 0 volt. What is VCE? Voltage between the collector and the emitter. So B stands for base. Now the ones who are first shy, you'll be doing this, don't worry. Second shy, third shy people who are joining. Today a lot of people actually wanted to join from everywhere in the country today. I think from Badulla, Trinco, Jaffna, a lot of people asked. So second shy people, watch. You know this. Base. First shy ones also watch. It's easy. Collector, emitter. Base, collector, emitter. So cutoff region. What about the saturation region? Saturation region is VCE is approximately 0. That means no voltage here. No voltage there. Then active region, VCE, this is the maximum, this is the minimum, greater than the minimum, lesser than the maximum. Maximum here is 10 volt. VCE is 10 volt. Right. So they're asking a suitable value for R to bias the silicon resistor in the active mode, in the active region. First, write these three. Cutoff, active, saturation. These are your conditions. These are your conditions. Right. Some of you all have messaged me now saying, sir, if you can show the curve. Right. This is your VCE IC curve. Collector current, VCE voltage. Right. Now remember, in the region, you will have variations like this. Now first shy ones, don't worry. These are all very summa cases. Very simple. Very simple. Second shy ones must have forgotten. That's right. Right. This region is called cutoff. This region is called saturation. This is called active. This is your output characteristic curve. Output characteristic curve. IC is in milliampere. VC is in voltage. This is your cutoff region. This is your saturation region. This is your active region. Okay. Right. Now they are questioning you on this part only. Don't worry about these two. If they ask you, you know VC is equal to VCC cutoff. VC is approximately 0, sometimes 0.1. So we normally ignore it. 0. There, 0. Active region, this is your value. Right. So they're asking you, what is the resistor you should keep here? What is the resistor you should keep here? Right. No beta value is generally given here. Beta values are not given. No. Right. Here, look. Look at this carefully. Now, current is flowing through here. Cutoff region means when it's equal to the maximum, current through this circuit will become what? 0. Current through this circuit will become 0. Cutoff region means current through the circuit will become 0. Right? And remember, when you're biasing a transistor, base emitter here is a silicon one. Base emitter is silicon means, be careful. They're asking what will R be. RB is this one. Base emitter is silicon. 0.7. Can you remember yesterday I drew a curve? Last MCQ. Silicon, the bias voltage, port bias voltage is 0.7. Germanium 0.3. Right. So here you can see this wire is empty. No resistor. So this is 0 volt. VB is 0.7. PB is 0.7. I'll show you here. VBE is 0.7. That means VB minus VE. Simple, lah? Simple. Voltage at E is connected to 0. So VB minus 0 is 0.7. Look. You all know this. Keep your eyes open. Some people are saying, "Ayyo, sir, we don't know." You know, man, this is easy. Look at this carefully. Whatever you need to know, I have taught you all now. You just make a note of it. Make a note of it. Right. These will erase also quickly. Right. Okay. Now look. VB is equal to 0.7. This voltage is 0.7. Have you seen this somewhere? This is 10 volt here. This is 0 volt here. Somebody is asking the resistor. I know the voltage here. Remember, when a transistor is biased to work, when it's working, no current, very small current. IB current is important. IB current is in microampere. What ampere? Microampere. Very small current will control this whole transistor. So we can ignore that current. And now we can apply potential divider method. Now you remember the potential divider? How do you find potential divider? From the 0 here, voltage 0.7. 0.7. How do you find it? Resistor into total voltage. Resistor into total voltage. Divide by the addition. Divide by the addition. R plus 100 kilo ohm. My God, kilo ohm. Yes. Now what? What are you going to do? Cross multiply this. Now you will say, sir, now 0.7. 0.7 means if I cross multiply this, then what? It's cross multiply and C will do first. R times 0.7. 0.7 R. 0.7 times 100. 70 kilo ohm. 70 kilo, no? 0.770. 70 kilo ohm. 10 to the power 3. That is equal to 10 R. Right. Take this to the other side. 10 R minus 0.7 R. 10 R minus 0.7 R is 70 kilo ohm. 70 kilo ohm, 9.3 R. 9.3 R. I am dividing 70 by 9.3. Think and tell. Assume 10 will. If I divide by 10, 7. 7 kilo. If I divide by something less than 10, is it more than 7 or less than 7? You can't calculate in MCQ. Tuck, 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 tuck. It should come. Tuck, tuck, tuck. 70 divided by 9.3, no. What do you know? 9.3 is difficult to divide, no. Divide by 10. 7 will come. 7 kilo. That if you divide by 10, no. If you divide by something less than 10, is it going to be more than 7 kilo ohm or less than 7 kilo? More or less? It should be more. More than 7 kilo ohm means 7.5 kilo. 7.5 kilo. Can you see? Clear, no? Perfect. Right. Moving forward. Moving forward. Right. Here you go. Figure shows how mass of fuel in a rocket decreases with time. Mass of fuel in a rocket decreases with time. So we know this question, 2003 A-level question they gave. Mass of rocket decreases, acceleration will what? Increase. Right. Now, atmospheric resistance is disregarded and the thrust produced is going to be constant throughout. Which of the graph represents the variation of the velocity with time? Think and tell. When the mass reduces, thrust is constant. Thrust is constant means what should happen? Acceleration should increase. Acceleration should increase. Then what will happen? Then what will happen? So what will happen? So here F is equal to MA. Think and tell. Some of you have on the equation it seems, right? Force is constant. Mass is reducing. To keep this constant, acceleration should increase. Acceleration increasing, graph number 5. Graph number 5. Okay. Graph number 5. This one. This one. A uniform solid cylinder cross-sectional area A, mass M. Let's mark the forces. Mg is there. When the vessel is raised up with constant acceleration, height of the submerged section is h. What will happen to the submerged section? Right before you do this, keep the beaker floating in water at rest. Let's call this h1. Here mg balances upthrust. Upward forces balances downward forces. Area I'll take as A, AH dg. That is equal to mg. Gg, we'll keep it like this. Remember, when it's accelerating, the pressure force acting here will also what change. Pressure force is changing means a resultant pressure force will change. Resultant pressure force will change means acceleration will what? Change. That means the upthrust here will be different. If you are writing this, let's say you are inside a lift. You are inside a lift looking at this. Observe this carefully. Sum of forces upward balances sum of forces downward. But is this the force? No, no. When you are inside the lift, you will experience a pseudo force also. So when this is accelerating upwards, there will be a pseudo force also downwards. Pseudo force, can you remember? Pseudo force acting downwards plus MA. What is your upthrust? A, H1, D. What is your resultant acceleration? Resultant acceleration is A plus G. Take M out, A plus G. What can you say? A plus G cancel off. Here GG cancel off. AHD equals M. Here AH1D equals M. This and this both are same. AADD H1 is equal to how much? H. Submerged height remains unchanged. What is the key point you should learn here? When this is accelerating, upthrust is also what? Changing. If you are observer inside, you will experience a resultant force downwards. Pseudo force also downwards. When you are going in the bus, you get thrown behind. Why? There's a pseudo force acting backwards. Equal opposite acceleration. From this, these two are equal. AADD same, H equals H. The submerged height remains unchanged. Submerged height remains unchanged. Write there small sentence. Write there small sentence. When it submerges, when the system accelerates, when the system accelerates, upthrust is also affected. Upthrust is also affected. Upthrust is also affected. Okay, right. Look at this carefully. As shown in the figure, P is applied to an object, 2 kilogram. Let's mark the forces. 2 kilogram is 20 newtons here. 20 newtons here. Coefficient of kinetic friction between the surface is 0.5 if the objects move with a uniform velocity. Uniform velocity means acceleration is how much? 0. Acceleration 0. The reaction force acting, be careful now. You can take components P cos 45. P cos 45 is in the forward direction. P sin 45 is acting downwards. And don't forget, there is friction acting on the surface opposing the motion. It's moving, so kinetic friction. What are they asking you here? What are they asking you here? What is the reaction force acting on the object? Be careful now. Be careful. Let me apply F equal ma vertically. Vertically, there is no motion. So you can say R minus 20 minus P sine 45, no vertical acceleration, R equals 20 plus P divided by root 2. Now apply in the forward direction. F equal ma in the forward direction. Who is pushing this forward? P cos 45. Friction opposite. Do we have acceleration? No acceleration. Here, P cos 45 is P over root 2. P over root 2. Minus mu k into normal reaction. Normal reaction, here you go. Equals 0. Look at the board. P divided by root 2 equals, take to the other side, 0.5. 0.5 is half. Normal reaction is 20 plus P divided by root 2. Now open brackets carefully. If you open brackets carefully, P divided by root 2 equals 0.5 into 20, 10. 0.5 into root 2, be careful, half into P over root 2, P divided by 2 root 2. Take this side, P divided by 2 root 2, that is equal to 10. Common denominator 2 root 2, 2P minus P, P divided by 2 root 2, 10. First multiply, P is 20 root 2. Some people make the mistake, the moment you see this, quickly you go and underline. Wrong. They want normal reaction acting. Normal reaction means substitute here. R is equal to 20 plus P divided by root 2. 20 root 2 divided by root 2. Root 2 cancel off. Correct answer 40 newtons. 40 newtons means answer number 5. 40 newtons means answer number 5. Okay, no? Answer number 5. Right. Write down the ones who need it. Okay, no? I'll slowly move forward. Huh? Right. Statement question. Huh. Two airmen. Who is airman? Air Force. Huh? Two airmen with different weights, different masses, are falling freely after jumping out of a plane. Maybe Independence Day celebration. Open their parachutes at the same altitude, same height, at the same time and start to descend. Whenever a question like this is met, remember, air resistance also you must think. Air resistance means when he is falling down, air resistance is acting in the upward direction. Right. Now look at this carefully. Initially, their speeds are reduced due to upthrust acting on the parachute. Initially, the speeds are reduced due to upthrust acting on the parachutes. Can this happen? Both the parachutes are identical. No, when they jump out of the plane, when these two fellows jump out of the plane, vertically starting from rest, their velocity will increase. Starting from rest, their velocity will increase. When their velocity increases, air resistance will act in the opposite direction. So mg is there, air resistance will act in the opposite direction. mg is there, air resistance is acting in the opposite direction. Have you seen a fellow jump from a plane with the parachute opening at once? No, no. The fellow falls down, then only opens the parachute. If you watch Discovery, they jump out of the plane, they do somersault, they are in the same location, they are moving from here to here, nicely move. That means they reach something called a terminal velocity. That means constant velocity. That means initially air resistance is only slowing them down, not upthrust. Statement A is wrong. Right there. When they jump out of the plane, air resistance will initially resist the motion. Air resistance will initially resist the motion. Air resistance will initially resist the motion. This will cause the speed to reduce first. Now they have different masses, m1, m2. The terminal velocity, terminal means upward forces balances downward forces. Upward force down, downward larger force, larger resistance. Larger force means it will fall longer. Smaller force means it will get shorter. Larger means it must fall some more to reach terminal. Smaller means lesser. That means if I plot the graph, who will reach terminal first? Lesser time, thinner fellow. Small man, body man reaches first. Body man reaches terminal velocity. Bigger fellow will take a longer time to reach terminal velocity. Clear? Clear, no? Right. B is correct. Terminal velocity is higher for the heavier man because he's falling some more, falling larger. Larger distance faller means even the mgh is large. Mgh is large means greater velocity, right? Both airmen reach the ground together. Hayyo can't. Why? This fellow is falling some more. He's falling with a higher velocity. Higher velocity reaches the ground first. Then statement C is wrong. Only B is correct. Statement A is correct. Right there. The heavier man has a larger terminal velocity. Greater the terminal velocity, quicker it will reach the earth. So the acceleration source are different. So somewhere like this. But shorter time it reaches terminal. Longer time it will reach terminal. Okay, no? Right. This one. Right. A person can just see the opposite edge of the bottom of an empty vessel, as shown in the figure, while keeping the eye in the same position. The vessel is filled with a clear liquid up to the brim. Then he is able to see a small mark at the center. The refractive index. Now be careful. Light rays are coming in. Normal here. Angle of incidence is I. Angle of refraction is R. vertically opposite if I take, vertically opposite if I take, here normal, this is your angle of incidence. Sorry, I can see the center, no? I can see the center. So here, I can see the center. Here light rays are coming from the center, this is I. If that is R vertically opposite, then this whole thing is R. Whole thing is R. Whole thing here is R. Look at this carefully. Light rays are going from the liquid. N liquid sin I equals Na sin R. Look at the board carefully. What is sin I? Sin I is equal to the small angle opposite over hypotenuse, R divided by this triangle hypotenuse, h squared plus R squared square root. Na is air, sin R is this vertical, this whole thing. Sin R is opposite to hypotenuse. What is hypotenuse? Pythagoras, 4R squared, whole thing square root. So here you have 2R divided by h squared plus 4R squared, h squared plus 4R squared. Simplify this. RR cancel off. NL is equal to 2 times h squared plus R squared divided by square root h squared plus 4R squared. Where do you see this? Only in answer number 2. Only in answer number 2. Okay. These things you have done in theory. Only in answer number 2. Right. Now, you can't say this is not there. Why? Curved mirrors you learned in O levels. Right. A thin square sheet PQRS is placed symmetrically along the principal axis of a concave mirror. Normally parallel rays will go through the focal. Light rays going through the center will keep on reflecting backwards. That's all. If P dash, Q dash, R dash, S dash represent the images of PQRS, then the image of the sheet formed by the mirror is represented by, let me draw ray diagrams. Right. Don't try to draw everything. For a few enough. Light rays from Q will go through the focal. Okay, no? Also light rays. Reversible you can draw. No? What do you mean by reversible? Light rays going through the focal will be parallel. Where these two meet, Q dash is formed. Then I'll use a different color. I want to draw for R. Light rays parallel go through the focal. Also, you can reverse that, no? Light ray going through the focal becomes parallel. What do you get here? R dash. Q dash, R dash are in the same line. Q dash, R dash are in the same line. Q dash, R dash, Q dash, R dash. Q dash, R dash, Q dash, R dash, right? What about light rays from P? What about light rays from P? Now, I hope you all drew this. Draw that below. Once you did not draw. Light rays parallel go through the focal. Light rays going through the focal will become parallel. Reversible ray I have drawn. Light rays parallel to principal go through the focal. Light rays through the focal will become parallel. These two blue rays will meet here, Q dash. Okay, no? Right. So I'll erase the rays, huh? I'll erase the rays, huh? Erase the rays, huh? Erase the rays. Right. Q dash, R dash is there. Right. Let me draw now again for P. Light rays going through the optical C will travel back along the same path. Light rays which are parallel to the principal will go through the focal. Here you will get P dash. P dash. Now what are the other one? I should use maybe dark green. What about S? Light rays going through the center, travels back undeviated, goes this way, comes back. Light rays going through the focal, becomes parallel. Here you will get Q dash. Sorry, S dash. S dash. S dash. S dash. Okay. S dash. One ray I forgot. Here the ray, right? Going through the focal goes parallel. S dash here. P dash, S dash is smaller, you can see. I didn't draw this perfectly, but R dash is somewhere here. R dash is somewhere here. And let me erase the rays. Let me erase the rays. You can see here clearly. You can see here clearly. R dash, Q dash is bigger. P dash, S dash is smaller. Smaller one. So P dash, S dash, R dash, Q dash. Answer is answer number 1. Answer is answer number 1. Okay. Right now. Right. Okay. Moving forward. The variation of the electric potential along the x direction. You remember, no? E is equal to minus delta V over delta x. Negative potential gradient. So here, negative gradient, zero gradient, positive gradient. Think, negative, negative becomes positive. Positive constant. Positive constant. Zero gradient means zero electric field. Positive means positive into negative, negative. Negative, there you go. Where do you see this? Positive, zero, negative. They are asking the force acting on the charge. Be careful. F is equal to EQ. E direction and force direction both should be what? Same if it's a positive charge. Have they said what charge? Positive charge. Yeah, there's said charge. Take it as positive. Take it as positive means then the variation is similar. Then the variation is similar. Similar means this is your answer. That's your answer. Right now. Right. Okay. Moving forward. Right. Look at this. As shown in the figure, a monochromatic ray of light is incident. Normally on one face, refractive index is given. The refracted ray emerge into air is best shown by, be careful. Here 45 means here also 45. Yeah. Here also 45. Refractive index is 1.4. So what is your critical angle? Critical angle is sine inverse 1 over n. 1 over refractive index. Look at the board and tell me. 1 over 1.4. Which angle is bigger? 1.42. This is 45. 1.4. Is this more than 45 or less than 45? Good answer. When here it's 1.4, will the angle be more than 45 or less than 45? Lesser means more. C is going to be greater than 45. That means total internal reflection does not take place here. Total internal reflection does not take place means light rays go from denser to rarer. Correct answer is answer C. Correct answer is answer C. So here you go your answer. Right there. Critical angle is greater than 45 degrees. Greater than 45 degrees. Greater than 45 degrees. Therefore, light rays will emerge into air. Therefore, light rays will emerge into air. Emerge into air. Okay. Light rays will emerge into air. You can see some small trick is given. Huh? Okay. What are they saying here? Now, this one, wherever you study, they would tell this is not there in the syllabus now. But I have taught you all why it's not in the syllabus as well. Yeah. So since this is done all island, I'll just give you a small hint. This is non-conducting solid sphere carrying. This is not there in our syllabus. But the variation of the gravitational field strength inside the earth, you should know. It's a straight line variation. There. So this is not there in your syllabus. Not in syllabus. There. Not in syllabus. But for your additional knowledge, the variation here is same as the variation of the gravitational field strength inside the earth. So inside the earth, gravitational field strength, gravitational fields guaranteed. You would have learned this. Variation of the gravitational field, straight line and curve. Inside straight line, outside curve. So this inside straight line, outside curve variation will come. From that you can see this is wrong, this is wrong, this is wrong. The only two options are this. If you put them together, electric field is a vector. This side positive, that side negative. This side positive, this side fields are negative. So here curve, positive curve, then negative side, straight line curve, straight line curve. So straight line curves will meet somewhere. Meet somewhere means most probable answer is answer number 2. Remember, this is not in your syllabus, but remember the variation for a non-conducting sphere. It is same as the variation of Earth's gravitational field, right there. Non-conductors are not in the syllabus. Non-conductors are not in the syllabus. Therefore, variation is similar to the gravitational field strength inside Earth. Gravitational field strength inside Earth. Okay. Right. Moving on. MCQ 18. MCQ 18. Right. A small dielectric slab is passed through an isolated pattern. Now tell me, capacitance will increase or decrease when there is a dielectric? Capacitance will increase. Capacitance will increase. Right. They are asking the potential difference. Now potential difference here, maybe you have to calculate. Q is equal to CV. This is positively charged, this is negatively charged. Charge will be constant. But when a dielectric enters, capacitance will increase. Capacitance increases to keep the constant, voltage will drop. So voltage drops. Once it goes out, again straight. Correct answer is answer number 1. Right there. Right there. Here, when the dielectric enters, the capacitance will increase. the capacitance will increase. The capacitance will increase. But the charge on the plates remain constant. Charge on the plates remain constant. Charge on the plates remain constant. So capacitance increases, potential drops. So the moment it enters, potential drops. The moment it goes out, potential is the same. Correct answer is answer number 1. Correct answer is answer number 1. Going up. Up. MCQ 19. That means this is the 59th MCQ. Huh? 59th MCQ. See, 60 MCQs are done this week. Right. A sound source emitting signals is at constant frequency Fs, moving along an arc of a circle. Arc of a circle. There you go. Right. A stationary observer is located at point X. You can see he's away from the center. If he's away from the center, if you're taking components, straight line, this is acute. If you take the component, it's like the person is going away. V cos alpha. Source is going away. Observer is here. Source is going away. Source is going away means frequency will reduce. Once this comes here, there is a perpendicular distance. Actual frequency, apparent frequency, both will be same. Once it comes here, this angle becomes acute. Take components. V cos beta. It's like the source is coming towards the observer. Frequency will increase. Here frequency reduces. Here frequency increases. Frequency at A will reduce. Source is going away. Frequency at B increases. Source is coming towards. That means your variation is answer number 2. Right there. At point A, if we consider the acute angle, it is like the source is moving away. 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 This means apparent frequency is less than the actual. Apparent frequency is less than the actual. And at B, it is like the source is coming towards. It is like the source is coming towards. It is like the source is coming towards. That means apparent frequency is more than the actual. Apparent frequency is more than the actual. Now this is electric fields. Electric fields, capacitors. This lesson, capacitors. There. Right. Going up. Finally. 20 MCQs done. We have 2 more questions, but 20 MCQs done. Right. Electromagnetic induction. They are telling you a metal rod AB is moving across this path. Remember, when the field cuts, there is going to be a current produced. Right? So if I draw this like this, location to location, if I mark it, location to location, if I mark it, remember the concept is slightly difficult, but try to understand it. These taught for the first shy students in I think few under magnetic fields. But the second one should know this. When a rod is going through a magnetic field, electromotive force is BLV. I'm taking it with a constant speed. V is constant. Same magnetic field. Then E is proportional to what? L. Can you see inside the magnetic field, length is increasing, no? Length is increasing means EMF is increasing. Then length is reducing. Can you see? Corner to corner here, length is reduced. Length inside the magnetic field is reduced. Increasing, reducing. It can't be a straight line variation. Why? These are not increasing linearly. So it's a curve. Correct answer 4. Right there. The induced EMF depends on the length of the conductor. Depends on the length of the conductor linking with the magnetic field. Linking with the magnetic field. Linking with the magnetic field. Here, the length gradually increases. Here, the length gradually increases. If the length increases, the induced EMF will also increase. But the length is increasing non-linearly. This length, can you say, I'll color it. Green. Are these linear increments? No. If I want, I can draw some more in between, just to make it easier for you. Here another one here. Here another one here. Here another one here. Here another one here. And then I can color it in green. This length to that length to that. This length to that length to that. Are these linear increments? No, non-linear. So correct answer is answer number 5. Correct answer is answer number 5. Okay. 4, sorry. Answer number 4. Right. Structured essay. Structured essay. Right. Be alert, huh? Today came from 8:30. Still going. You all also can go with me. Okay? Work with me. Don't worry. There is nothing called tiredness. It's just your mind. Huh? Nothing called tiredness, just your mind. Right. Right. Okay, no? Back again. If you are sleepy, go quickly have a glass of water, come back, focus. A student plans to carry out an experiment using a sonometer to determine the frequency of a tuning fork. Frequency of tuning fork, right? Frequency of tuning fork. Okay. Where should he place the sounding tuning fork to obtain resonance? Where should he place? Where should he place? Now remember, sonometer box is here. One is a fixed bridge, other is a movable bridge. We are keeping the peg or paper rider there. So remember, ideal location to vibrate is vibrate and keep it between the pegs. The energy is going to be transferred uniformly. Okay? Energy is going to be transferred uniformly. Right there. We vibrate the tuning fork and place it between the center of the pegs, or bridges. Center of the bridges. This will uniformly distribute the energy to the wire. This will uniformly distribute the energy from the box to the wire. From the box to the wire. Okay, no? From the box to the wire. Right. What procedure must he follow to obtain the fundamental resonance? What should he do? First one. Bring the bridges. Bring the bridges closer to each other. And place a paper rider. Place a paper rider between the bridges. Between the bridges. Correct, no? Between the bridges. Vibrate the tuning fork. Vibrate tuning fork. Place on the sonometer box. Place on sonometer box. Between the bridges. Between bridges. And move one bridge. One is kept fixed. One bridge. Until paper rider flies off. Until UNTIL. Until paper rider flies off. Paper rider flies off. Now when paper rider flies off, what do? Measure the distance between the bridges. Measure distance. Measure distance between bridges. Between bridges. When paper flies off. When paper flies off. Actually, what you should do is, when a paper flies off, repeat the experiment and check and measure the length and then get the average length. Yeah. Try this first. Try this first. Right now, I'm sure you are reading this. Put a star and write. To get an accurate measurement for the balance length, to get an accurate measurement for a balance length, we repeat this experiment. We repeat this experiment for the same tuning fork. For the same tuning fork, and we measure the balance length. And we measure the balance length and get the average value. And get the average value. Okay. Get the average value. Right. A student measured the fundamental resonance length corresponding to different tensions of the sonometer wire using different weights. Write down an expression relating MI mass per length of the sonometer wire. Right. Write an expression relating all of this. Okay. MT, yeah. Okay. So fundamental resonance is 1 over 2L square root T over simple M. 1 over 2L tension becomes capital MG over simple M. From this you can get the frequency. From this you can get the frequency. Okay, no? From this you can get the frequency. Right. Which of these experimental L values is considered to have a highest accuracy? Larger the length, greater, smaller the fractional error, smaller the fractional error, greater the accuracy. Right there. Larger the length or larger length. So here the answer is larger length. Larger length. What's the reason? Larger length, lesser error, or we can say lesser fractional error, lesser fractional error, lesser fractional error, therefore more accurate. Therefore more accurate. There you go. More accurate. Right? In this experiment, graph plotted by the student is shown in the figure. Graph plotted is shown in the figure. Graph plotted is shown in the figure. Straight line has not come. Straight line has not come. Unfortunately, straight line has not come here. So if I show it here, if I show it here, 605. 605 it goes through. 605 it goes through. I'll draw this and give, don't worry. 605 it goes through. What else? It goes through 7850. 7850. 7850. Here you go. Goes through that. What else? What else? Okay. 100 also I think it goes. Right. So a graph is like this. It has not got printed, no? That's the problem. 100 goes through that. Right. mark with arrows a suitable place. Mark with arrows a suitable place where we can use to find the gradient. You must find a location where it exactly crosses the grid. These three locations are suitable. Any one you can take. Any one you can take. 1 and 100. 5 and 600 here. 5, 600 is also good. 1, 100 is also good. X-axis. X-axis. 7, 850 is also good. 7, 850 is also good. One of the two. One of the three. Right. Okay, that's all. That's all they're asking. Right. Next one. So here, if you look at it, look at the graph now. F squared m kilogram. F squared m kilogram. So if I rewrite this, I want the equation. F squared is equal to 1 over 4L squared. 1 over 4L squared simple M G times capital M. This graph is of the form y is equal to mx. Let me complete this. This is your gradient. Now, can you find the gradient here? I have found it now. We can find the gradient. How to find the gradient? Gradient is equal to G divided by 4L squared simple M y2 minus y1 divided by x2 minus x1. That's how the gradient is found. y2 minus y1. I'll take two far off locations. y2 minus y1, 850 minus 100 divided by x2, 7 minus 1. G divided by 4L squared simple M. 750 divided by 6. G divided by 4L squared simple M. This is going to be 750 divided by 6. Be careful now. This axis is centimeter squared. 750 centimeter squared. This is 6 kilograms. 6 kilograms. So you have found a relationship for the gradient. Now G is 10. G is 10. Yeah. G is 10. How will you simplify this? Simple M. 4L squared at the bottom. Here 750 centimeter squared. 6 kilogram. Look at this carefully. Here, if you want to find simple M, make simple M the subject. Simple M the subject means 60 divided by this comes. 60 divided by this comes. From there you can find the required answers. Okay, no? So here be careful. Here ms minus 2. If you want, you can cancel this off. Here this is going to be kilogram per meter. Kilogram is there. Convert others to meter. 10 to the power minus 4. 10 to the power minus 4. Length should be in meter. And these ms minus 2. From this we can find simple M. Okay, no? From this we can find simple M. Right. Essay question. This is what they are telling. Now, a empty 2 kilogram copper vessel. Best is draw it. Empty 2 kilogram copper vessel. Copper vessel is there. Empty 2 kilogram copper vessel. Empty 2 kilogram copper vessel. If hold it. With a lid is at a temperature 150 Celsius. Is at a temperature 150 Celsius. Right? Is at a temperature 150 Celsius. 0.1 kilogram of water at 30 Celsius is poured into the vessel and lid is closed. Right? Lid is closed. Right. So here 0.1 kilogram of water at 30 degrees Celsius, this is 150 degrees Celsius, is poured into the vessel and we close the lid itself. And we close the lid itself. Here you go. What's happened? Who will give heat? Vessel will give heat. Who is absorbing heat? Water will absorb heat. There. Water will absorb heat. Look. Final temperature of the vessel and water become less than 100. Producing a mixture of water and vapor at 100. Converting all the water into steam at 100 or higher. Assume that water boils at 100 degrees Celsius. Water boils at 100 degrees Celsius. And no heat lost to the surroundings. Okay. I think we can do this here. Right. Consider the first possibility. What is that? Becoming less than 100. Let's see. Let's see. Heat given. Who is giving heat? Calorimeter is giving heat. Mass of copper, specific heat capacity of copper, change in temperature. Mass of copper, 2 kilogram. Initial temperature 150. Water becoming less than 100 degrees. Water becoming less than 100 degrees. Okay. Less than 100 degrees. Let's see. Specific heat capacity of copper 400. Nah? Specific heat capacity of copper 400. Latent heat of vaporization 210 to the power 6. Specific heat capacity of water is 4000. Right. Look at this carefully. Look at this carefully. Heat is given. Heat is given. Mass into specific heat capacity. Change in temperature. Copper is giving. So reduces. Heat absorbed. Who is absorbing heat? Water. Mass of water, specific heat capacity of water, change in temperature of water. This is change in temperature of copper. What is mass of water? What is mass of water? Mass of water is 0.1 kilogram, 30 degrees Celsius. 0.1 kilogram, 30 degrees Celsius. Right. 0.1 kilogram, specific heat capacity 40,000. 30 degrees Celsius means temperature increasing, theta minus 30. No heat loss to the surroundings. Heat given equals heat absorbed. Heat given equal heat absorbed. Let's see below what is heat given. We have calculated no. 800 into 150 minus theta. Heat absorbed 400 into theta minus 30. Right. Let's work. Once you get here, simplify it. 2 zeros, 2 zeros. 4 times 1, 4 times 2. Open brackets. 300 minus 2 theta. Theta minus 30. Right. Now what? Take it this side. You get 330. 330, 3 theta. 330, 3 theta. That means theta is equal to 110 degrees Celsius. 110 degrees Celsius. What are they saying? Show that this is not possible. Statement 1. Statement 1 is what? Statement 1. Final temperature less than 100. Is it less than 100? No. 1 is not possible. 1 is not possible. Simple work. 1 is not possible. Right? Okay, no? Heat given equal heat absorbed. Right. What's the second case? Producing a mixture at 100. That means it will stop at 100. Hence, so this is what really happens, right? So heat given, yeah, assuming second one is correct, heat given equal heat absorbed. So initially 150 degrees Celsius, these are 2 kilogram. I'm pouring 0.1 kilogram of water at 30 degrees Celsius. Finally, I'm getting water and steam at how much? 100 degrees Celsius. Mass of water, I don't know, M1. Mass of steam, I don't know, M2. But M1 plus M2 is equal to 0.1. Okay. So heat given again by the vessel. Mass of the vessel 2 kilogram. Specific heat capacity 400. 150 minus final temperature is 100. Who is absorbing the heat? Water is absorbing the heat. Remember, from 30 degrees to 100 degree water, all will increase together. All will increase together. That means the complete 0.1 will increase. 0.1, 4000, change in temperature is 100 minus 30 plus. Who will vaporize? Not everything. Only a small part will vaporize. X amount will vaporize. Steam will also form. Steam will form not for everything. Here 0.1, here 0.1, only for X. X will vaporize. 2 10 to the power, I think 6. I can't remember the value. I think 6. 6. Let's see whether this is true. Let's see whether this is true. Simplify. 800 into 50. 400 into 70. X into 2 to the power 6. We'll find the amount of mass. If this is less than 0.1, correct. 0, 0, 0, 40. 40,000 minus 28,000. That is equal to X times 2 to 10 to the power 6. Here 12,000. 12,000 equals 2 10 to the power 6 times X. Here 2 times 6,000. 6,000 10 to the power minus 6x. Be careful. Huh? Minus 6 means 1, 2, 3, 4, 5, 6. 0.06. 1, 2, 3, 4, 5. There's another 0. 0.006 kilogram. That's okay, no? Less than 0.1 kilogram. Second method is possible. Second method is possible. Second method is possible. So you can write here method 2, method 2, method Roman 2 is possible. You have shown that the amount that became steam, that means M2 here, actually M2, actually M2. Here, you put X, no? I'll remove the X, I'll put M2 below. I'll put M2 below. Here M2, here M2, here M2. Finally also here M2, here M2, here M2, here M2. There you go. Then what else? Then what else? In order to make the third possibility a reality, what is the third possibility? Converting all the water into steam. Converting all the water into steam. Well, the superb. Think carefully. Think carefully. What are you going to do? What are you going to do? Determine the mass of water required. So, right. Heat given. Heat given equals heat absorbed. What is happening? Water at 30 degrees Celsius becomes water at 100 degrees Celsius, completely becomes steam at 100 degrees Celsius. Complete mass, 0.1 kilogram, 0.1 kilogram, 0.1 kilogram. Everything becomes. So heat given is by the calorimeter. 2 kilogram, 400, 150 minus 100. Steam, no? Heat is absorbed. How much water you must pour? M times Specific heat capacity of water. Change in temperature 100 minus 30 plus. Everything will vaporize. M times 2 10 to the power 6. Here 800 multiplied by 50. Here M 400 4000 multiplied by 70. Here M 2 10 to the power 6. Here you have 3 zeros 1 2 3. Here 3 zeros 1 2 3. Simplify this. 40 equals 280 M plus 3 zeros here means 3 zeros here. Only 3 zeros left. 2000 M. 40 divided by 2280, that's the mass. 40 divided by 2280. Somebody here divide and tell me what's the answer. Somebody tell me. What's your answer? What's your answer? It's 1 over 57 kg. How much? How much? Divide and find. 0.018 kilogram, I think Bilal is telling us. Bilal, no? Yes, Bilal is telling us. So I'll accept his answer, 0.018. Okay, no? Right. Any more? Nothing. Right. Week 1 done. 60 MCQs, 3 essays, 3 structured, done. Now the remaining essays. I told you, no, after the 4th week, the 5th week, that I will give. All the other now, next week, 2001 paper. Tomorrow I'll put it. Other week, 2002 paper. The other week, 2003 paper. After that, we'll collect everything. The remaining structure and the essay so far that you have done will do. Next week, 2001 paper, same intensity, even better. You and I, we're going to do this. Okay then. Stay home safe. Good night.